So, all right, so this was picking up what we did last Thursday. Last Thursday we started talking about collisions. So real quick recap, we learned that there are 3 different types of collisions. Elastic is a collision in which the objects don't stick and the kinetic energy is conserved. Inelastic collisions, where they don't stick but some kinetic energy is lost. And then completely inelastic collisions are where they stick together. All right? And what we had done was on Thursday, we went through and we did an example of an inelastic collision and a completely inelastic collision, but we've not yet done elastic. So that's what we need to do today. All right? So we talked about all this stuff. We talked about the fact that, remember, the conservation of momentum is a result of the third law, right? Because when objects interact, they exert equal forces on each other for equal times, so they have the same change in momentum. Whatever's lost by one is gained by the other. Does that ring a bell? We good? Okay. All right, so we did example number 1 already. We decided it was inelastic, right? Because we had lost some kinetic energy because both vehicles slowed down. We did example 2 where they stick together. Remember, you guys, the trick for the ones where they stick together is you just set their final velocities equal to each other. So that we had 1250 VF plus 750 VF because they both have the same VF. Good? Cool? All right, so that's in 10 seconds, a quick run through of what we did last Thursday. Does anybody have any questions before I go on and do elastic? All right, cool. All right, so here's the deal, elastic collisions. So if you look in your book gives you all these equations about elastic collisions, and they're crazy complicated, and I couldn't even begin to dream of memorizing them. I could memorize them if I had to, but I mean, like, it wouldn't be practical to memorize them long term, in the same way that you can memorize F equals MA, right? Okay? So, I mean, if you want, you can go back and look at the equations in the book. I have not found them super useful as I've been solving the problems. All right? Instead, I'm going to show you something that I am weirded out isn't in your book, but I think is more useful and probably more reasonable to expect you to memorize. Okay? So, here's the deal. Elastic collisions have a special property. So I'm going to go through a whole bunch of algebra. All right, so buckle up. All right, so here we go. So the first property we have is this. Number 1. So any collision has, assuming you've just got 2 objects, so I'm going to keep things simple here, and we're going to assume it's just 2 objects, that the change in momentum for object A is equal and opposite to the change in momentum for object B, right? In other words, whatever's lost by one is gained by the other. Okay? So if you write that out in notation, using symbols, it becomes this. The mass of object A times its change in velocity, is equal and opposite to the mass of B times its change in velocity. Okay, so again, that's true of any collision. Elastic, inelastic, completely inelastic, whatever. Good? Okay, now, property number 2 is elastic collisions has your total kinetic energy before the collision has to equal your total kinetic energy after the collision, right? All right, so we're going to use this to come up with another big long expression about mass and velocity of the vehicles and see if we can simplify down to something that is useful. Okay, so before I do that, was that a hand up in the back? Okay, everybody good? All right, so total kinetic energy initially. Well, that means the kinetic energy of object A initially plus the kinetic energy of object B initially equals the kinetic energy of A after the collision plus the kinetic energy of B after the collision, right? Follow? Okay, so kinetic energy is 1/2 mv squared, right? So this becomes 1/2 the mass of A times the velocity of A initially squared plus 1/2 the mass of B times the velocity of B initially squared equals 1/2 the mass of A times the velocity of A final squared plus 1/2 the mass of B times the velocity of B final squared. Everybody good? Questions? Pretty good. All right. I can multiply everything by 2 and the 1/2s go away. Good. So now what I'm going to do is I'm going to group it. I'm going to put all of my B's on the left side and all of my A's on the right side. So if you do that, you get this. Let's see. So I'm going to subtract MA squared from both sides. I'm going to subtract MA squared from both sides. And I'm going to subtract MBVBF squared from both sides. Good. I thought that that's the best way to write that, but you can see these are going to cancel. So here I'm going to be left with. All right. Like I said, it's not algebra. Am I going too quick? Are we okay? You good? Are you hurt? Are you good? You're working ahead, aren't you? Hurt? Yeah. No, I'm just making sure I wasn't leaving anybody behind. Okay, so these cancel out. So on my left side, I'm going to have the mass of B times the velocity of B initially squared minus the mass of B times the velocity of B final squared equals, on the other side, my B's cancel out, and I'm left with the mass of A times the velocity of A final squared minus the mass of A times the velocity of A initial squared. This is why I don't usually do derivations. I just say, here's what the equation is. This one I felt like was important enough. All right, what can I do on the left side, you guys? Factor out the mass of B, right? So we get the mass of B times the velocity of B initial squared minus the velocity of B final squared. And on the other side, I have the mass of A times the velocity of A final squared minus the velocity of A initial squared. We're almost done. Sorry? It's not quite the same because these guys have squareds, and the top guy doesn't have those squareds, but you're totally in the ballpark. We're going to pop a negative on one of those to flip them around. All right. What's A squared minus B squared? It's the difference of squared, right? A plus B, A minus B, right? Right? You guys remember that? A squared minus B squared is the same as A minus B times A plus B, right? Difference of squares. Good. So here I've got, oh, difference of squares. Oh, difference of squares. Okay, so let's kind of box this off just so we remember how we came to this conclusion. So here we go. So this is going to become, oh, I did not want to change colors there. So we get the mass of B times VBI minus VBF times VBI plus VBF, right? Equals the mass of A times VAF minus VAI times VAF plus VAI. All right, this, like Alex said, is the same as negative mb times vbf minus vbi, right? That's sloppy. Minus vbi. Everybody good? By switching, pulling out a negative? Times vbi plus vbf equals the mass of VAF minus VAI, VAF plus VAI. If it helps, this is the last time we'll ever have to do this. All right, now, what do you notice about this thing and this thing? Yeah, that is, all right, so look at the things that I just underlined with the green brackets there, you guys. Now, look at what we set up here in number 1. Oh, those things are the same, aren't they? So I can divide both sides by those, and what do? They cancel out, right? So we're left with this. The velocity of B initially plus the velocity of B final is equal to the velocity of A initial plus the velocity of A final for any elastic collision. So, in English, if you take the initial and final velocities of your objects and add them together, you're going to get the same thing. You know what I mean? The initial plus final velocity of A is equal to the initial plus final velocity of B, regardless of what the mass is. Good? Only for elastic collisions. Okay? Memorize that. Okay? That will not be on your AP equation sheet, but it is something that will make your life way easier. Good? All right, so, great. Why do we care? All right, so, solving an elastic collision is basically solving a system of 2 equations. This is going to be one of your equations, and then the conservation of momentum equation is the other one. Okay, so, any questions about all this giant mess of algebra? You're like, no, it doesn't matter. I know the end result. That's all I need. And you're right, largely. All right, here we go. So, example 3. Same numbers we started with before. Okay. In the first example, I gave you the final velocity of one of the vehicles. I don't remember which one, but whatever. In the second example, I told you they stuck together, and so we knew they had the same final velocity. In this one, I'm not giving you the final velocity of either vehicle. All I'm telling you is that it is an elastic collision. Okay? So here is how we do it. So we're going to come up with 2 equations. Well, so first of all, you should make your drawing, right? So I'll do this kind of quick. We've already got this. So mass of the truck, 1,250 kilograms. Velocity of the truck initially is 5 meters a second. What's wrong? Okay. Velocity of the car initially is negative 8 meters a second. And we're looking for the final velocity of the truck and the final velocity of the car. So there are 2 unknowns, right? There are 2 velocities, and I don't know either of them. So there are 2 unknowns, and thus we need this, velocity of truck final. Sorry about that. Right, so I know they're going to collide, I know their starting velocities, but I don't know the final velocity of either object. So there are 2 unknowns, so I have to have 2 equations, right? Make sense? All right, so here are my 2 equations. Sorry, I'm just trying to decide what order I want to write them in. All right, so equation number 1 is the conservation of momentum. Conservation of momentum. Conservation of momentum tells me that the total momentum before the collision equals total momentum after the collision. So it's this. It's 1250 times 5 plus 750 times negative 8 equals 1250 times the velocity of the truck final plus 750 times the velocity of the car final. Let me pause there for a moment so you can absorbify that and make sure you understand it. Right, this is the total momentum before they collide, right? Mass times initial velocity plus mass times initial velocity. That's got to equal the total momentum after the collision. Mass times final velocity plus mass times final velocity. Good. All right. So equation number 2. It's elastic, which tells me that the velocity of the truck initially plus the velocity of the truck final equals the velocity of the car initial plus the velocity of the car final. So let's plug in our numbers. Let's see, so we're going to get 5 plus the velocity of the truck final equals negative 8 plus the velocity of the car final. So now we've got 2 equations, 2 unknowns, solve it. So there are a bunch of ways you can do this. My thinking is let's take that bottom equation and solve it for one of the 2 variables, and then plug it into the top equation. Make sense? All right, so here we go. Let's see, let's add 8 to both sides. We'll solve for VCF. So we get 13 plus the velocity of the truck final equals the velocity of the car final. So now I'm going to take that mess and plug it into equation number 1. So equation number 1 becomes, well, I can certainly, let's see, 1250 times 5 is what, 5,000, 6250? Minus 750 times 8 is 6,000. Equals 1250 times the velocity of the truck final plus 750 times the velocity of the car final, but that's this, 13 plus VTF. So a lot of numbers to keep track of, but you know, it's all linear. There's no quadratic formulas or integrals or anything crazy. It's just do the algebra. This is about as hard as these get. So, any problems? Okay, so 6250 minus 6,000 gives us 250. That equals 1250 VTF plus. Oh, I get written on my paper. Duh. Wait a minute. Why do I have? Oh no, I did it a different way on my paper. 750 times 13 gives us 9750 plus 750 VTF. So 250 equals 1250 VTF, and 750 VTF is 2000 VTF plus 9750. So subtract 9750 and you get negative 9500 equals 2000 VTF. So VTF turns out to be negative, whatever 9,500 over 2,000 is. 4.75, very good. That's good, because I did it a different way, but got the same answer. What's that? That did not. Well, I started with them and then straight. All right. So is everybody good with how we did this? So now the velocity of the car final was 13 plus VTF, right? So that's 13 plus negative 7. Oops. Oh, why do you hate me? Don't answer that. Negative VTF. Just wrote the same thing twice. 4.75, there we go. And so it gives you what, 8.25? How could we check it?
Do it in real life.
My car's nothing fancy, but Mickey, what do you got? Okay, good. We can double check VI plus VF equals VI plus VF. What do you say? So the change in momentum equation's a better word because that's what we use to start this. Oh, the change in momentum equations. Gotcha. So really, that's those two equations. The change in momentum for A is equal to the opposite of the change in momentum for object B. You can algebraically rearrange that in one step to get total initial momentum equals total final momentum. They're really the same equation in disguise, just by rearranging them algebraically. What kind of collision was this? Elastic. What does that mean?
Kinetic energy.
It means our kinetic energy should be conserved. So you could check and make sure that your initial kinetic energy equals your final kinetic energy. But Mickey's exactly right. Based on our algebra, that should be the same thing as making sure that our velocities add up, and we know they do because we used that fact here to find one of the velocities. So it should work, but probably worth going and checking if you were, if you had a few extra minutes and this was, like an AP question. Go back and check it. Questions? All right. So that's about as hard as they get. Yeah, they're tedious and they're long, but they're not. Same thing, these collisions happen so quickly that even if friction was a concern, it would be negligible in such a short amount of time. Perfect. Good? Yeah, Alex. I promise it's not.
They can never both increase in speed, right?
Good, tell me why. Okay, good. Now, there is a condition under which that might happen.
Springs.
Good. If we had some sort of energy that was released upon impact.
So
Like a spring that was compressed and then when they hit, it releases.
Or it could drop the speed of light and mass converted into energy.
Right, exactly. Well, there's that too, obviously. I figured that one without saying. Alex?
No, I was
You say the same thing? Speed of light? Gotcha. Good. Glad we're on the same page. All right. Is everybody good with this? All right, cool. So, oh. All right, so I think the last thing we got to do is two-dimensional collisions. That honestly, it's the exact same thing as what we were just doing, but there are more numbers to keep track of. Because now instead of just keeping track of x, you got to keep track of x and y. All right. There will not be a ton of these. The ones that you get are very basic. What's that? I have not seen any that have z, but it would just be the same thing. You would just do one more dimension. All right. So, oh man, sorry, my board needs to be calibrated. So. All right, so if you're dealing with a collision in two dimensions, you literally just use conservation of momentum along each of your axes. If it was elastic, you'd apply conservation of energy equation. That equation that I gave you, the VI plus VF equals VI plus VF, still holds. So they give this example here. So let's talk about this example conceptually. All right, and then we'll do a real example with numbers. All right. So the idea in this example is this. So mass 1 is moving horizontally, and it's going to hit mass 2, which is stationary. All right. So before the collision, this object has momentum in the x direction, but in the y dimension, there's no momentum, right? So my total momentum horizontally is just m1 v1, right? My total momentum vertically is 0. Good? Exactly. So the marble's going to go, bam, it's going to hit this guy, right? One ball is going to get pushed down, the other one's going to get pushed up. Okay? Now, Alex just said it, but what should be true about the vertical component of this guy, this is momentum, and the vertical component of this guy's momentum? They should be equal and opposite, right? Because they have to add up to 0. Okay? And then their two horizontal momenta, I hate that, but it's a word, have to add up to the initial momentum of this, right? Make sense? And then, if you knew your angles, you could go from there. All right, so let's do an example, and then I think we're done. All right, so in this one, both of the objects have a mass of 2 kilograms, which makes it possible to take some shortcuts, but I'm going to not take the shortcuts because I want you guys to see how you would solve it if the masses were not equal. All right. In retrospect, I wish I'd gone back and rewritten this problem and changed the mass, but it didn't occur to me until it was too late. Okay, so here we go. So two kilogram bodies, A and B, collide. The velocities before collision are, and you're given these two unit vector notation velocities. And then it says after the collision, the velocity of A is this, and you're trying to find the velocity of B after the collision, and then the change in kinetic energy. All right? So we're basically going to follow the same process that we did in that very first conservation of momentum problem that I gave you guys. All right? I'm going to make a little chart. Okay? So here's object A, here's object B. All right? So initially, let's see. So the velocity of A initially is, sorry, my handwriting's going to get worse because my board is becoming uncalibrated. So you get 15I plus 30J, right? And so the velocity of B initially is negative 10I plus 5J. These are all meters per second. Good? Now, it's not velocity that's conserved, it's momentum that's conserved. So I can find the momentum of each of these, right? Well, momentum is just mass times velocity, and my mass is 2 kilograms. So that means that the momentum of A initially should just be this times 2 kilograms, right? So it's going to be 30I plus 60, right? Yeah, okay, sorry. J, kilogram meters a second. See if this is even worth doing. I don't know if that helped any. We'll see. All right, we can do the same thing over here for B. Let's find the momentum of B initially. It's going to be its mass, 2 kilograms, times the velocity. So you're going to get negative 20I plus 10J. Units here are kilogram meters a second. Follow? All right. After the collision, oh shoot, sorry. I'll leave myself a little space so that we can deal with kinetic energy in a minute. So I'm leaving one blank line there. All right, final. Let's see, the velocity of A final is negative 5I plus 20J meters a second. So I can find the corresponding momentum just by multiplying by 2, negative 10I plus 40J kilogram meters a second. And the question wants to know this guy. All right, so that's basically what's given to us. I did a couple just simple calculations, right? I found some momentums. Momenta. All right, so conservation of momentum says what two things are always equal? Change in momentum for one object is equal and opposite to the change in momentum for the other. So one thing I could do is I could find the change in momentum here. So I would do negative 10 minus 30 and 40 minus 60. That would give me the change in momentum for object A. I could reverse it and add those to B. Okay, that's fine, but because of the negatives, I tend to prefer personally to think in terms of the totals. So I'm going to do it that way. If you want to do it the other way, there's no reason why you couldn't. So my total momentum initially, well, that's going to be these guys added up. So 30 plus negative 20 is 10I, and then 60 plus 10 is 70 J kilogram meters a second, right? So that's my total momentum before the collision. Make sense? Everybody see what I did there? I just added component-wise, right? All right, so what should my total collision be after the collision? Same thing, 10I plus 70J kilogram meters a second. Oh, so now I can find out what I'm missing over here for B, right? Follow? So negative 10 plus what is positive 10? 20. And 40 plus what is 70? Oh, 30. So there's my momentum. That's the momentum of B final. So now what should I do? Find the velocity by dividing by mass, right? So divide everything by 2, you get 10I plus 15J meters a second. And there's your velocity. And that's question A. Yes?
Just throw the velocity vectors into the equation. Oh, it's not elastic.
Oh, okay. Well, so we don't know if it's elastic, which takes us to question B. Let's find the change in total kinetic energy. No, don't be sorry. That's exactly why we're going over this. Are you good?
Yeah.
So, go, brain, think. Okay, so total kinetic energy. So kinetic energy is 1/2 mv squared, right? So for this, shouldn't v squared just be 15 squared plus 30 squared? Right? Because I've got my x component is 15, my y component is 30. A squared plus b squared equals c squared. Follow or no?
Yeah.
Did I lose anybody there? Okay. So that means that my kinetic energy here, I'll do it in blue so you guys can kind of see what's going on. My kinetic energy is half of the mass, which is 1, right? Right? So it's just going to be 15 squared plus 30 squared. So technically, you'd take the square root of that, then square it, and plug it into 1/2 times m, times v squared. So anyway, so you get 1125 joules for that. If you don't understand the shortcut that I took here, you can certainly go back and do this, and you'll see what happened here. Like, you know, draw out this vector, find the hypotenuse, and do 1/2 mv squared, and you'll see what happened. Okay? All right, same thing here. So 10 squared plus 5 squared, you get 125. So that means my total kinetic energy before the collision is 1250. Down here, my kinetic energy is going to be 425. 5 squared plus 20 squared is 425. Down here, my kinetic energy is going to be 10 squared plus 15 squared, which is 325. For some reason, I can never remember what 15 squared is. And so my total there is what, 750? Joules, joules, joules. So what's our change in kinetic energy? And we went from 1250 down to 750, so our change in kinetic energy is negative 500 joules. So elastic? No. The only way it would have been elastic is if that had been 0, right? We lost energy. Cool? Questions? All right, do you guys see what I'm saying? This really is just like, you could have, if you had wanted to, solved this problem once and just looked at the x-coordinates. And then you could have gone back and solved it again and just looked at the y-coordinates. That's what we just did here. But I just sort of did the x and y coordinates at the same time. Simultaneously, if you prefer. Good? All right then. I'ma shut up. So that's, I think, it for this chapter. So that gives us a really good chunk of time throughout the rest of the week for me to answer questions for you guys.